Okay, today we're going to be looking at continuing our work on partial fractions, but what happens when we've got a repeated factor. So for example, I've got a quadratic over a cubic, because the cubic is ax plus b and then times cx plus d all squared, and the setup, and actually the setup will actually look like that, but I'm just going to take a little bit of a time to show it. It's going to be constant over the first bracket, the linear, and then what we do with this repeated, we have constants in each case, so it's going to be something over cx plus d to the power 1 plus a constant over cx plus d squared. And the reason is, if I sort of go backwards a step, I'm always going to have that a over the ax plus b there, and then plus, if I consider this as one fraction, cx plus d all squared, I get b times the cx plus d, and then plus that c. I've got to be careful with my big c's and little c's and so on like that. And going back a line before, I've still got the a over the ax plus b. And then here I end up with bcx plus bd plus c over the little cx plus d all squared. And all that is, that's just a linear expression. It's as if we take this quadratic over cubic and split it up as the first bracket and then plus, let's call it mx plus n over that thing squared. So these constants here for particular values can be split up like this, so where m equals b times c and n equals b times little d plus little c, like that. So we end up with something x plus something over that thing there, and we can do some algebraic long division. But basically, our setup is that we end up like that. Constant over linear, constant over the repeated factor to the power 1, constant over repeated factor to the power 2. Very, very occasionally, you'll see a question where the repeated factor is actually cubed. If it's cubed, I'd end up with b over the bracket to the power 1, c over the bracket squared plus d over the bracket cubed. Let's have a look at how we apply that then to a couple of examples. We've got nice straightforward linear over cubic, x plus 1 over x minus 1 times x minus 2 squared. So we do our setup. So a over the x minus 1 plus b over the x minus 2 and then plus c over the x minus 2 all squared. Now, when we get rid of our denominator, please be aware we're not multiplying by that and that and that. We are multiplying by this. This is our lowest common denominator. We're getting rid of it. So when I multiply by x minus 1 and x minus 2 all squared, then I've got to think quite carefully what I've got on this side. So if I'm multiplying by all that lot, I've got the x minus 1, I need the x minus 2 squared. Plus b times, I've got 1 of the x minus 2, so I haven't got an x minus 1, and I haven't got 1 of the x minus 2's. And then plus c, I've got both of those, but I haven't got the x minus 1. So what's going to happen, when I stick x is equal to 1 in, it's going to eliminate the b and the c term to help me find a. When I stick x is equal to 2 in, it's going to eliminate the a and the b term to find c. How then do I find b? Match up coefficients. Something along those lines. So x equals 1. Gives me 1 plus 1, 2 equals a times minus 1 squared, 1. A equals 2. Nice and straightforward. X equals 2. So x plus 1 is 3 equals that 0, c times 2 minus 1, 1. C equals 3. And I can't avoid using at least one of those to find b. Let's match up coefficients of x squared. There's none on that side. I've got a times x squared there, so it's a plus b, so b is whatever minus a is minus 2. And that's it, that's my answer. So my original function, whatever it was, is now 2 over x minus 1 minus 2 over x minus 2 plus 3 over x minus 2 all squared. And that's it. What then the question tends to go on to, it could be integrate these things, or do binomial expansions on these and lump it all together. Second example, pretty much the same method as the first. slight twist because I've only got over x on the bottom, but it's a ordinary fraction because it's quadratic over cubic, so I can write it as a over x, b over 2x minus 1, and then plus c over 2x minus 1 all squared. The only slight issue that I might have as I do this, I've got fractions for x, so I've got to be careful with it. Same deal, get rid of the denominator, multiply by this common denominator here to get 4x squared minus 3 is equivalent to a. I've got the x, but I haven't got the bracket squared. B, I haven't got an x, I've only got one of the brackets, so I need another one. And then plus, I could squeeze in there, cx. So x equals 0 gets rid of two of them. Minus 3 equals, that's 0, that's 0. I've got a times minus 1 squared, a, one go. X equals a half is my other one. 4 times x squared is 4 times a quarter, so 1 minus 3 minus 2, that's 0, and c times a half, so c equals minus 4, and then match up, x squareds again, because it's in there, it's in there. Be careful with this one because I've got 2x all squared, don't forget, so I've got 4 on that side equals a times 4, and then plus 2b. So 2b equals 4 minus 4a plus 12 equals 16, b equals 8. So my fx in this case is going to a minus 3 over x plus 8 over 2x minus 1 and then minus 4 over 2x minus 1 all squared. That's my function.